So today's experiment is about to study the damping coefficient or damping factor for of a damping media for an oscillatory system, or you can say this is a to study the damped vibration. So damping is an external influence which we generally apply on a system, mostly on oscillatory system, and it reduces or restricts the oscillations or prevents the oscillations. In actual systems, damping is generally produced by processes that dissipates the energy which is stored in the oscillation. For an example, if you have seen viscous drags in mechanical system or resistance in electronic oscillators, there are also damping which are not based on mechanical energy loss, and they happen in biological systems. Now, there are brakes available which use some kind of fluid. They all absorb some kind of energy. In fact, if you take the example of this spring and you attach one load on the end of the spring, then this load itself acts as a some as a media which reduces the oscillations of this spring. Okay, so you provide oscillations to spring without load, and with load you will see that the spring with load actually comes to a static state earlier than the spring which is not loaded. Now here in this experiment, we will study the damping ratio. The damping ratio is a dimensionless measure, and it shows that how the oscillations in a system decay after a certain disturbance. So many systems exhibit oscillatory behavior when they are disturbed from their position of static equilibrium. Like this example, we have already seen that a mass when suspended from the spring and it might be pulled or released, bounce, it goes up and down, and on each bounce the system tends to return to its equilibrium position but overshoots it. So sometimes losses like frictional losses, they can cause oscillations to gradually decay or to attenuate. Just like a laser beam attenuates in fluid, uh, the vibrations or oscillations can also get attenuated with some media. So in this experiment, we will study the damping coefficient of a media actually. So you will see there is a shaft, and then this shaft is given some oscillatory motion while certain part of the shaft is kept into some media. Due to the presence of this media, the oscillations of this shaft actually damps. So if we try to plot the damp, it will be something like this. So the first vibration will have higher amplitude, and then slowly this amplitude of vibration will decrease, that you will see during the experiments. This is nothing but a classical example of how the oscillations or the vibrations may decay. And it has also been found that the decaying occurs and it closely follows the logarithmic uh, functions, certain logarithmic functions. So on the basis of those logarithmic functions, we can actually model the decay of this kind of oscillation. So in order to determine how this decay is happening, A logarithmic decrement function delta is generally used, which is defined as the ratio of log of two amplitudes, which are just close by. So let's say if here it is x1 and here it is x2. So this is x1 by x2, just consecutive amplitudes. Then this delta is here is defined as logarithmic decay. And the damping ratio or the damping factor of this fluid or the media or the damping capacity of this media is generally defined by term zeta, and it is nothing but uh, ratio of logarithmic decay over 2 pi. So this damping factor zeta, it defines how much effective the damping media is. So for an example, if we use water in the tank and if we use oil in this tank, the decay process will differ. So in oil, the decaying may happen faster than in water. So there are certain kinds of liquid which absorb this kind of oscillation, and their performance is measured by the term damping factor. So here in this experiment, you will compare the damping factor for water and oil maybe, or maybe with air also you can compare in order to determine the effectiveness of certain media. So that's all for this experiment. And also you will have to plot certain graphs. For an example, the logarithmic decay versus depth of immersion. So this depth also affects the process. This equation here, this damping factor is just a simplification of already existing equation. Zeta is also called damping ratio as well as damping factor, and it actually characterizes the frequency response of the oscillations. And this has a lot of application in control, in absorbing of energy in automotive sectors. This damping media is used in a lot of applications. Without water or without any media, the case when this is called undamped, you know? And for the undamped system, the damping factor or damping ratio is equal to 0. Okay? For undamped system, zeta is 0. And then there are cases of underdamped, although we need to go into much more detail what is underdamped. But for the cases when zeta is between 0 and 1, then this case is called underdamped. Similarly, there are overdamped when zeta is greater than 1. So you also need to find out whether your zeta is greater than 1 or not. So if your system is overdamped or underdamped. And when zeta becomes 1, it is called critically damped. So that's all for this experiment. Vidit, do you want to add anything?
No, sir. I guess this is it, sir.
Okay.